Does anybody have questions from homeworks to this point before we dive into the new stuff here? Take a minute for questions. Okie dokie. Well, maybe next time we'll get some. So today we're going to start section 15.4. We're going to do this over 2 days. So we're just going to do a little bit today and we'll do a little bit next time and try to space this thing out before you get just buried under an avalanche of assignment. Since the last time was a pretty big homework set assignment, and this one won't be super small either, so we're going to break it into 2 chunks so it's a little bit more manageable for y'all. So in 15.4, we're really not going to be handling any new content, so to speak. It's going to be just using the tools we've developed over the past 3 lessons. So it's just like an applications piece now. So remember in the sections 1 and 2 when we wanted to solve an exponential equation, we had to like go to our calculator, graph it, and find the intersection? No more. We're going to develop the algebraic tools here, or collect the algebraic tools that we've developed, and talk about how we can start solving these exponential equations and also logarithmic equations by hand, algebraically, without having to resort to our calculator. So for the most part, we're just going to look at some example problems and kind of talk through how to solve them. And that's going to basically be our day. I have like 5 or 6 examples. Typically, it takes around 30 to 35 minutes to kind of buzz through those, being, careful. And then you take the rest of the time in class to kind of get chipping away at these homework assignments. Sound good to you guys? Probably be a similar theme on next class as well. I guess it'd be Friday. Today's Wednesday, right? I think so. All right. So what we have here is an exponential equation. I can tell it's an exponential equation because the variable is located in the exponent. So as we developed in the previous section, the key to solving an exponential equation is going to be canceling out the base of the exponent, in this case, that 1/3. What operation is going to cancel out an exponent base? We've been talking about it for about an entire lesson. It starts with an L. It's a logarithm. So that's going to be our key tool here that we're going to be using. But before we can do anything with a logarithm, I have to get that exponential part or piece all by itself. So this equation says 14 times 1/3 to the x minus 1. My first order of business is to get that 14 out of here. How do I get that 14? Get rid of it? Divide both sides by 14. So far, so good. Now, as we saw in the previous lesson when we talked about logs, there's lots of different logs, right? You can have log of almost any base you want as long as it's a positive number not equal to 1. So when I take the log of both sides, I can really use any log I want if I don't care about things getting ugly. But I do care about that. My life is hard enough. I don't need to make this harder on myself than it needs to be. So I want to be careful about which log I choose to use here. Does anybody know which log I should do to both sides for this particular equation? I want to use log base, not 3, close. I'm going to use log base 1/3 because I want the base of my logarithm to match the base of my exponential. That is going to make things algebraically the easiest it can be. And my life is hard enough. I got like a job and responsibility and my daughter and a wife and a house, like taxes to pay, yeah, bills and stuff. My life is complicated enough. I don't need to make it any harder. So I'm going to choose to do this the easiest way possible. Since I have the choice, I will sign up for the easy way. Yes, thank you. Work smarter, not harder, guys. Everybody feel okay so far? So log base 3 cancels exponent, or log base 1/3 cancels exponent base 1/3. Whoop, whoop. So they just cross out. So I'm left with just the x minus 1 from the exponent. And then to get the x by itself, what do I need to do? Add 1 to both sides. Now I can't add that 1 inside the logarithm. So just tack it on to the end or whatever. And now it's calculator time. So remember, to get the log where I can pick the base, I need to press the math button and then scroll all the way down and choose the log base command. And then I can just type this in exactly like it looks like on my sheet of paper. And I get -1 for my answer. How's that feel? That's not so bad, right? It's like, okay, basically the same process for solving. Yeah, I got to use a logarithm in there, but it's the same idea. We're just like using it to cancel something out, just like we've done before. Like when we solved trig equations or whatever, and we had to use like the sign inverses to cancel the signs. It's like the same idea. So not too bad. Let's do another example. This is basically the same problem with just different numbers, right? First step I'd want to do is divide by 12, yeah. Now, I recognize looking at this that 27 divided by 12 is 9/4. If you didn't recognize that, though, it doesn't really matter because it's all going to go into your calculator anyway. But it's like 2 less digits that I have to write. And I am efficient in that way. And I'll use my brain power a little bit to have to write 2 less digits. But like if you didn't see that, like it won't matter. Everybody's okay? Now that we got the exponential by itself, we'll do the log of both sides. Which log base do I want to use here? 3/2. I don't know why I wrote a 7 there. That was 5. Sometimes it's hard to talk and write at the same time and do it correctly. So, whoop, whoop. Log base 3/2 cancels exponent base 3/2. It's a wonderful thing. So to get the x all by itself, the last thing I need to do is multiply by 5. Again, I can't multiply the 5 inside the logarithm. So I'll just tack it on to the outside. And now it's calculator time. If you have your own calculator with you, I'd encourage you to follow along and practice doing this. Oops, I forgot to write the times 5 at the start, so I'll just tack it on at the end. It doesn't really matter. Just got to make sure it's outside my parentheses there. But I get a 10. How we feeling so far? Hopefully this feels pretty straightforward here. I don't know if I want to call it easy or not, but it doesn't seem very complicated. Now, let's look at another type of exponential equation that's fundamentally different than the ones we looked at before. So take a look at this exponential equation. What about this exponential equation makes it fundamentally different than the ones we looked at previously? What should you notice in here that's a cue to us that this is going to go differently than the previous ones? Very good. I have x in 2 different places, right? I have an x in 3 to the x, and I have another x in 3 to the negative x. Everybody's okay with that? So that's the cue that there's going to be a kind of a different type of solving procedure. Okay, if I have x in just one exponent, things should move very similarly to what we've just done. If I have it in more than one exponent, it's going to be a fundamentally different process. So the first thing I would do is I'd start by getting rid of the fraction, because Lord knows it's going to be complicated enough without the fraction rattling around in there. How am I going to get rid of the over 4? Yeah, just multiply both sides by 4. Yep. So far, so good. Now what I want to do is I want to get rid of the negative exponent, right? I have that 3 to the negative x. I don't like that negative exponent in there. What can I multiply by both sides of this equation to get rid of that negative exponent? Well, negative 1 times 3 to the negative x is just going to be negative 1 times 3 to the negative x. The negative doesn't go into the exponent, right? What? Nope. Mines are going to be below here. It's 3 to the x. So that's going to distribute through. Let's see why, because maybe that's not entirely clear. So 3 to the x times 3 to the x is just going to be 3 to the x squared. When I multiply 3 to the x times 3 to the negative x, the exponent, or the base of the exponential, stays the same, and then we add the exponents, right? What's x plus negative x? 0. And what's 3 to the 0? Just 1. Does everybody see why 3 to the x was the one that we needed there? Now that you've seen that trick, easy to apply it. Okay, I just use the positive version, whatever it is, and knocks it out for me. So take a look at this equation right now. When I look at this, I see, okay, I have something squared plus a constant equals a constant times that thing, right? Looks kind of like a quadratic to me. You guys see it? So that's what I'm going to do. I'm going to just say, okay, well, let's replace those 3 to the x's with just a different variable name. And then it'll just be a quadratic. Everybody, if you couldn't see it was quadratic before, it sure as heck is quadratic now, right? There's no mistaking that. To solve a quadratic equation, what's the first thing I need to do? Not divide by itself.
No, Y by itself.
Oh, you got well, you don't want to get y by itself because you have two y's.
Y squared.
You need to get everything on one side. It needs to equal 0. Really, for any polynomial equation, getting it equal to 0 is a great idea. So to solve that quadratic, the two primary techniques I would use in this situation are the quadratic formula or factoring, right? Now, I'm going to take a quick check to see if I can factor it since the leading coefficient is 1. If I can factor it, it should be easy to factor. Are there two integers that multiply to give us positive 1 and add to give us negative 8? Nope. What's that tell me? The quadratic formula is where I should be living here. But I want to give at least a passing attempt to factor it. So the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So when I do that, I have 8 plus or minus. Negative 8 squared is 64. 4 times 1 times 1 is 4. 64 minus 4 is 60. So I have square root 60 over 2. But guys, we're not done. We're trying to solve for x. What have we solved for? Y. So now we have to go and put our x back. Remember, y is equal to 3 to the x. So we can say 3 to the x is equal to 8 plus or minus root 60 over 2. So far, so good. Now, since it's a plus or minus equation, I can really just think about that as two separate equations. One of them with the plus, the other with the minus. Everybody feel good? And then how do I get the x all by itself then here? What do I need to use? Not a square root. Not division. A log. Very good. Which log base should I use? 3 should match the base of my exponential. Oops. So we should have x equals log base 3 of the stuff. And then it's just calculator time, right? So when I type those in, I'm going to get about positive 1.88 and negative 1.88. If you have your calculator out, why don't you take a quick second and try to punch those through and make sure you get the same result that I do. I would encourage you to use the horizontal fraction bar on this problem because the parentheses are kind of nasty if you don't do it that way. Did it work, calculator punchers? Excellent. All right. Let's look at some logarithmic examples, and that'll be that. So we just saw probably the hardest, I think the most complicated examples. I shouldn't say hardest, let's say most complicated. Maybe before we move on, let's just kind of rehash what we kind of did here. So the first step was kind of turning that into a quadratic equation. Then we had to solve that quadratic equation. Then we turned it back into an exponential. And then solved it. Right? So that was kind of like our, that was kind of like our general outline of what we were doing there. Anytime you get one of these exponential equations that has x's in more than one exponent, though, that's the general idea. You want to make a quadratic, solve that quadratic, turn it back into an exponential, solve the exponential. So I think that kind of helps from a meta view of kind of what is the process we're trying to do here, so that the work is a little bit more, a little easier for us to remember and what to do and how to follow it. All right, let's look at some logarithmic equations. So I have 2 more examples for solving some logarithmic equations, and we are done. So the key idea for solving a logarithmic equation, what's going to cancel a logarithm? An exponent base, right? Now, any exponent base should work, but which one is going to be the easiest one to use? The one that matches the base of our logarithm, right? So just like for the exponential equations, before I do that, though, I want to get that logarithm all by itself on one side. So what should I do to start on this problem? Divide by 3. Now, when I look at my logarithm and try to decide the exponent base, I don't see a base written down for my logarithm. Oh no! But if you remember, this was one of those special cases, right? We had a special name for this. This is called the common logarithm. When I don't write a base down, what base do I remember it means? When there's no number on the base of the logarithm, it doesn't mean base 1. In fact, logarithms can never have base 1. The bases have to be positive numbers that are not equal to 1. When there's nothing written there, we remember that it's 10. This is log base 10. So the exponent base I'm going to use to both sides is 10. And now I know I'm writing these comically big 10s and everybody kind of snickers at it. But I'm doing that on purpose, really to emphasize the fact that we're not multiplying by 10. We're using 10 as the base of an exponent, so it's the left-hand side, or 10 to the power of the left-hand side equals 10 to the power of the right-hand side. So, whoop, whoop. Exponent base 10 cancels log base 10. So I'm left with x squared is equal to 10 squared. So we square root both sides. Yep. When we square root both sides of the equation, what do we have to get? Plus or minus. Very good. So our answer should be plus or minus 10. Everybody good there? But wait, we're not done. All logarithmic equations must be checked for extraneous solutions. So the check, though, is quite easy. All we need to do is take our answer. So like if I take negative 10 and plug it back into the original equation, I'm just checking to make sure I get a positive number inside the logarithm. So negative 10 squared is 100. That's positive. We're good. If I take positive 10 squared or positive 10 and I plug it in, positive 10 squared is 100. We're good. Both of these answers check out. There's no extraneous solution here. Everybody feel okay with that? Pretty rare to get an extraneous solution when you have x in only one logarithm. Uh-oh. Mr. Kulik, is that like, are you hinting at like what the next example is going to look like? You better believe I am. Let's see an example where I have x's in more than one logarithm. Again, this will be presents us with a fundamentally different problem than the previous one. Just like when I had x's in more than one exponent, it was kind of a fundamentally different problem. So my goal here to start, I have 3 different logarithms, right? Everybody see that? My goal is to turn that into one logarithm. What's the name of the process I use for turning lots of logarithms into a single logarithm? You did in the last homework set. Starts with a C. Compress or condense. Yes, those were the 2 terms we used. Very good. I think the directions in the homework say condense, so I'm going to use that word, but compress would be fine. To do that condensing, we need to use our properties of logarithms, product, power, and quotient properties. What is the order that we look to use those properties when we do condensing? We go power to product to quotient. The order of using those properties would be an excellent thing to put on your half sheet, right? Not that it's hard to remember, but if you screw it up, like you're going to make a big mess for yourself. All right, so I'm going to start by simply moving all the logarithms onto one side. So I'm going to subtract that 2 natural log of x from both sides. So I have all the logs on one side. Everybody feel good? Okay. First thing we look for is the power property. So when we're condensing the power property, we're looking for coefficients in front of our logarithms. I see one of those. The power property allows me to move that coefficient outside of my logarithm and turn it into an exponent inside my logarithm. Then we'll look for our product property. So when condensing the product property, what you're looking for is the sum of 2 positive logarithms. What the power property allows us to do is rewrite that sum of 2 logarithms into the product of a single logarithm. And then last, we look for the quotient property. That's the difference of 2 logarithms. And the quotient property allows us to write subtraction outside our logarithm as division inside our logarithm. Everybody feel good so far? So we've got this condensed into a single logarithm. So now we're ready to cancel out our logarithm. What cancels out a logarithm? An exponent base. So let's look at the base of the logarithm. Oh no, no base is written here. It says ln. What is the base for ln? Yes, that means log base E so what exponent base are we going to do to both sides? We're going to do E. And exponent base E cancels log base E. Whoop, whoop. So we're left with oh my gosh, that was an x squared. I just forgot the squared. My apologies. How come you guys didn't yell at me about it? Sheesh. What type of equation are we left with? This is a rational equation, right? Just like we did handled in the last chapter. To solve a rational equation, we want to clear fractions. So I want to multiply both sides of this rational equation by the least common multiple of the denominators. What is the least common multiple of these denominators going to be? Not 1, x squared, right? It's the only denominator. Yes, sure, Sam. Sure. Okay. So to solve this, it's got to equal to 0, but I might as well FOIL this thing out first before I go ahead and subtract the x squared over so I can just combine any like terms at the same time. I'm just going to do that foiling here real quick. So now if we subtract x squared from both sides, we got that. So far, so good. It's a quadratic equation. So I could solve this by either the quadratic formula or factoring. Since the leading coefficient isn't 1, I'm not even going to try to bother factoring it, because even if it can factor, it's going to be kind of time consuming. I'm just going to use the quadratic formula. This one does factor, by the way, in case you're wondering. But it just hardly seems like it's worth it. So again, negative b plus or minus square root b squared minus 4ac all over 2a. Negative 5 squared is 25. 4 times 2 times 2 is 8, is 16. 25 minus 16 is 9. The square root of 9 is 3. So just knock that all down there. So if we add these, I have 5 plus 3. That's going to be 8 over 4. So that's 2 is one possible answer. Then 5 minus 3, that's 2 over 4. So 1/2 is my other possible answer. But we're not done. We still need to check. So I'll take my answer of 2, go all the way to the original problem. If I plug it in, 3 times 2 minus 2, that's going to give me 6 minus 2, that's 4. That's a positive, that's great. 2 minus 1, that's 1, that's positive, great. 2, that's positive, great. My solution of 2 works. I accept that answer. Now let's check the 1/2. 3 times 1/2 minus 2. 3 times 1/2 is 1.5. 1.5 minus 2, that's negative. I'm stopping right now. I discard that guy as extraneous. So as soon as I get one of them that works, or one of them that's not positive, I'm done. Everybody's good with that? FYI, 0. Is 0 positive? No. So if I get log of 0, that's bad too. That's also extraneous. Just to point that out there. When we say positive, I mean positive, not non-negative. Right? 0 is not included in the positives. So that's it. That's the gist of it for today. Look at that, 36:07, right on time, Mr. Kulik. So this next homework set that we're going to add, 99 through 130, that went in on top of the 37 through 68, 71 to 98 from last time. I know these were a lot, but I gave you guys like, we're going to have 40 minutes, 45 minutes here to work on stuff. Same thing tomorrow. I'm trying to slow down a little bit so that the homework doesn't stack up like ridiculously. And some of these problems are quite quick, once you get the hang of it. But this is also the first time you guys are doing this. So like, I think we kind of need, you need to do the practice because it's not like we're doing this again for the first or for a second or third time. Yes, sir.
37 through 130, that's due on Sunday?
Yeah, this is for this Sunday.
Sounds good.
Yep. And seniors, this is your last homework assignment from the book. You also have a Delta Math next week, but those are your last 2 homework assignments. I would point out to you, seniors, that if you have 100% in the homework category, and there's 2 dropped homework assignments, that what's going to happen if you don't turn in the last 2 homework assignments? Nothing, right? They'll just be your 2 drops. So if you're a senior with 100% in the homework category, your grade will not be affected if you do not turn in the last 2 homework assignments. Just pointing that out there to you. Now, is this stuff going to be on your final exam? Yeah. Should you do it? Yeah. But just do it enough to where like, okay, I get the idea. I'm just not going to worry about, I'm going to pick and choose and just do a couple of them that look kind of hard, make sure I can do it, and feel like that's good enough. You know what I'm saying? Just reminding you guys about what's going on. Seniors, have you started your review packets that I passed out? No, maybe a little bit, some of us. Again, reminder that that's due the last day of class. So I think on the B day, that is the May 1st is our last meeting.
Yeah, what day are we going to take the final procedures?
I think it's on the 2nd is the math final. So again, like, make sure that you guys have that, turn that in. If you have questions on it, definitely ask. If I'm you guys, I probably want to have most of it kind of tried to knock that out before spring break, because you think you're taking it with you on spring break to work on? I think the odds of that are pretty low. Because you only have, what do we have, like 3 days or 4 days or something before, once you're back from spring break, before the year ends. I think 4 days. Seniors, that is. All right. I'm going to stop talking now. Everybody good? Seniors, you have a clear picture about like what's left to do, what you're responsible for, all that jazz.
See the drop